and atoms. Entropy is really, okay, for the most part, it's a measure of the number of ways of distributing the thermal energy among the atoms of a system. Okay, so it's a measure of the number of ways. So if W is the number of ways, then the entropy can be defined as directly proportional to the natural log of W, where this proportionality constant K here is known as Boltzmann's constant. So the more ways you can distribute energy, the thermal energy among the atoms of a system, then the higher the entropy. That is why when you increase the energy, okay, there would be more ways of distributing it, as we shall see in a little while. Okay, so what happens if all of the atoms are at their lowest possible energy? So they don't have any thermal energy. Okay, zero thermal energy. All of their energies, you can say, is potential. What would be the number of ways you can distribute nothing? If I've got $0, how many ways can I distribute $0 among all of you atoms in this classroom? One way. You all get nothing. That's the only way, right? So number of ways of distributing nothing is one way. What's the natural log of 1? 0. That's why it's convenient to define the entropy at absolute 0, where you don't have any thermal energy to distribute, to be 0. Okay, so entropy is 0, and there's only one way of doing things. All right. So what are the factors then that affect entropy? We said when you heat something up, that the entropy increases, right? Well, if you have more thermal energies, then there's more ways of distributing the thermal energy. That means a higher entropy. Let's look at an analogy to make this easier to grasp. If I have, let's say energy is money, okay? Let's say I'm distributing energy, so I'm distributing money. So I'm going to distribute nickels between two people. Okay, so Michelle and Jessica. Okay, so I've got 3 nickels to distribute between you two. Okay, first of all, I have 2 nickels, 3 versus 2 nickels. If I have 2 nickels to distribute between you two, okay, so I have Michelle and Jessica, all right? How many ways can I distribute 2 nickels between you two? Okay, you each get 1, or Michelle gets 2, Jessica gets none, or Michelle gets none and Jessica gets 2. That's 3 ways, right? But what if I have 3 nickels? I can give Michelle 3 and Jessica none. I can do 2 and 1. I can do 1 and 2. I can do 0 and 3, right? So there's more ways. And you can see if I even have more nickels, I'd have more ways of distributing them between you two. All right? So increased thermal energy leads to an increase in entropy. Okay? Now, the other factor is quantization of energy. You've learned in Chem 105 that energy is quantized, right? Atoms and molecules can only have certain allowed energies. They're not going to just have any amount of energy. Okay, there's restrictions on how much they can have. It's like saying, okay, for our analogy now, we're going to be picky. We're going to say Michelle is picky. She's only going to accept pennies. She's not, okay? And so let's say Michelle and Jessica are picky. They're only going to accept pennies. Or, no, they're not picky. They'll accept pennies. So, and let's see. Augustine and, what's your name back there? Callie and Augustine are picky. They'll only take nickels. Okay, so quantization, so pennies versus nickels. So I can't give you anything other than 5 cents or 10 cents, right, Callie? And Jessica and Michelle, I can give them pennies. Okay, same thing. I have 10 pennies versus 2 nickels. That's 10 cents either way, right? How many ways can I distribute 10 pennies between 2 people? So Jessica and Michelle again, 10 pennies. 10 and 0. Well, 10 and 0. Or I can give you 9 and Jessica gets 1. I can give you 8, Jessica gets 2, and so on, right? It's a lot of ways. Between Augustine and Kelly, I only have 2 nickels. So 10 cents versus no cent, right? 5 cents versus and 5 cents, right? And 0 cents and 10 cents. Fewer ways. So the bigger the gaps between the allowed energy levels, the fewer ways you can distribute the thermal energy. So the bigger the gaps, that means they're more picky in terms of how much energy they can accept. Or so that that factors into the amount of entropy the system can have. Okay? So in general, the more free, this is one thing you'll find in quantum mechanics, the more freedom of movement the atoms have, okay? We associate that with the notion of disorder. The more freedom of movement atoms have, the closer their energy spacings and the higher the entropy is, okay? So you can see this one right here, the 2 people who would accept pennies versus the 2 people who would only accept nickels, you get a higher entropy for the people who would accept pennies. Okay? So the closer the energy, the more the freedom of movement, the closer the energy spacing. So let's